aerospace department. In a dedicated time, I would like to present our recent, if I may call it, achievements in something that we've been doing for past decade, meaning the stability of general rates, but recently the orthotropic. You can on that. Okay, I can use maybe. Okay. Sorry about it. So generally, the plate stability is an old and ancient problem. It's nothing new. It's been around since even the first days of flights, and it's been actually investigated by many engineers and analysts through decades because it can cause actually fatal crashes of your flying with vehicles. So that's it. To prove that, actually, we can see several pictures right here. I don't know, here since the early days of flights to history, some contributed to this plate instability. This is not Wright brothers. It's actually even before them, Langley's plane. Here we can see even on the modern plates, F-117 crash due to so-called flutter, which is nothing else but the plate instability. How does that look in a real life? Let's see maybe a short movie just to emphasize the, I can bring it here. Pay attention to the satellites. They should be straight and flat. If not, the fatal crash that can cause actually the loss of guidance. There you lose your aircraft. This was only shown to show how actually the importance of this problem, And it is not that we cannot deal with these problems. Actually, the state of the art is here. We know how to tackle these problems. There are several approaches: analytical, numeric, experimental, or flight testing. Each of this has its own benefits and its own drawbacks. I'm just guiding towards something that we'd like to propose. This is, for example, a typical analytical approach, so-called binary problem. It is efficient, it can be applied, the equations can be solved. The problem is it requires actually numerical analysis, which takes time. Usually in these problems, time equals money. You need people, you need computers, and so on and so forth. And the results are so-so. Also, we are very familiar with the numerical approach, where we need to build several models in order to simulate this phenomena. We build structural models, aerodynamic models, and in the middle, the so-called spline models, which connects these two. So there's no problem there. Also, this approach, more accurate than the previous one, also requires time, requires quite a few actually analysts at the same time. Finally, we have the experimental approach. These are actually the screenshots from our experiments. I don't know, maybe you'll be in a position to see. This is our wind tunnel here in this building. Maybe tomorrow, I don't know. And our setup for this particular problem, and this is one orthotropic plate, E-glass that we were investigating when we were developing the software based on the ML for this phenomenon. Right, I would like to draw your attention. How does this look like? Again, here, you get some flow. Sample, and we are actually trying to relate the axis of stability. This is actually the regular one. So when we combine all of this, this is the full process, the full algorithm, what we have to do before we render some structure flying rescue. We have to go through all of these steps in order to, whether is it manned or unmanned, we, based on this, this is something that in real life we need to go. It all requires time, it all requires resources. So this is how we do it today. The results, just to compare different approaches, they are more or less there compared to the reference one that we have seen. Let's say that is around, for a particular configuration, around 20 meters per second. The other models, all of them are here listed in a graphical form. So more or less is there. This was all shown to, first of all, emphasize the importance of this problem. Again, it can lead to the loss of the aircraft. Second of all, it is not that we are in the dark, that we don't know what to do. We can calculate this. So what we are doing, and what is actually the emphasis of this presentation, would be why have we chosen actually to go towards new approaches. Basically, everyone is talking about the AI these days, but AI, believe it or not, has been around for ages again, right? So the goal, actually, what was driving us was actually to speed up the analysis process, to be in a position to investigate different geometries and materials, in other words, designs in a shorter time. This all has an impact to reduce costs of our projects. So generally, machine learning is a part of AI, and in general mechanical engineering has a very good potential. The very first step would be, for a particular problem, first of all, to recognize the problem, then to select the particular algorithm. If there is no algorithm, then you first need to develop it. The problem selection is, like we've seen in a previous presentation, if I'm not mistaken, it would be like image recognition. This is actually value prediction problem, because we are trying to predict the flutter speed, the loss of stability for a particular geometry. For these type of problems, generally speaking, the regression algorithms are suitable. So at the very first stage of our investigation, we have concentrated on these particular algorithms on this for this particular problem. The second very big problem is you really need a good data set, good quality data. Yeah. How to come to that is a problem of its own. It usually requires quite a lot of elements to which actually you're going to apply your algorithm in order to establish certain relations and come to a satisfactory results. In this particular problem, this is actually what we did. We have used so-called the hybrid approach. Hybrid means in order to create your data set, which, as I said, is the problem we're solving, we use the experimental data from the tests in our wind tunnel with the analytical approach. There's nothing wrong with the experimental data. This is the actually quality data. And if generally you can do that, this is the one that you should opt for. However, this is very expensive, not only because it takes time, it takes resources in energy terms, but also it requires time to build your samples. That's the problem. So this hybrid approach in recent years is actually gaining in its popularity, because you generally create a data set, generally expand the experimental data with the analytical results, and you combine them all together in order to create a relatively large amount of items in your data set. And then, as I stated earlier, a second problem is the algorithm selection. In this case, as I said, we were actually interested in regression algorithms, because in some other problems they have shown very good results for, as I said, the value recognition problem. In this particular problems, we have investigated quite a few, but no algorithms, fast forest, SDCA, fast3, LBFGS, and light GBM regression. All of them were actually programmed and apply it to a particular data set in order to obtain the results. Again, the speed at which the loss of stability occurs. When this was done, it was relatively easy to implement. We have developed the software using the latest ML.NET technologies. How did we actually decide which algorithm is the most suitable for this particular problem? We were actually increasing our data set by adding the items using the analytical approach until I have set this to this R-squared value, which actually shows you how good your data fit is, 2.95. Under number 7, as you can see, this light GBM for this particular problem, it does not mean that it is good for all the others. Almost show excellent correlation, unlike the others. Unfortunately, the duration of actually investigation of the data set was quite long, but this is something that we have to realize. And the important thing is that this is the advantage that this you do only once. Once you get these results, you are done, and you can start using it. So for this, again, particular problem, the light GBM regression showed to be the most efficient, but for relatively large data set. So without any modifications to it, it is modern algorithm, but relatively known, and quite a few papers were written on this particular. Its most advantage, unlike the others, is that it builds its tree in a horizontal way, unlike the others that are building it vertically and trying to form like a tree. That's why you see name tree in most of these gradients. So now, when we deployed it and programmed it in our software, we of course compared it to results of this particular algorithm with other conventional methods that I have mentioned earlier. First of all, the numerical one, which is considered to be the most accurate, as you have seen in one of previous slides. Here in gray, I know it's a little, the font is small. However, here it reads that it's 20.8. For this particular geometry, the loss of stability appears at 20.8 meters per second. This is almost something that we have seen in the wind tunnels of the experiment that I have shown you again on the previous slide. And this is the result as from our newly developed ML model. Here in red, you can see it's 21.08. So basically, there is no difference. What would be the advantage of this approach? This was obtained instantly. Very little population. Of course, after training the data set, as I said, but you do that only once. This takes about 7 hours to compute relatively fast. This, as I said, this is the experiment. So I can't say, but you really need to build a sample, you really need the resources, you need a wind tunnel. So again, the advantage of, as I said, this approach, and after going through this loop, would be this: you obtain basically for free in an instant of time, and then you can continue investigating other geometries, basically quite different. Where we are actually going, like again in the previous presentation, we also have to satisfy certain standards. This is one of the modern standards in a nation, European standard, that relates to Flutter. And as they require, you see, they require any rational analysis. Rational in this case means all of these previous conventional ones that are ML still not irrational. We are trying, actually, we hope that this approach that we are proposing would be considered in the near future as a rational analysis, if I have actually convinced you that this system might work. This, of course, is not perfect, like nothing in life. Now we believe that ML can be used for the stability problems, that this algorithm is a good candidate to be actually investigated further. Unfortunately, for more complex geometry, it won't work. If there's something nonlinear, it cannot recognize it. And also, which is actually one of the big drawbacks of this approach, is that there is no extrapolated values. This really means that you really should know the bounds of your problems. If it's something outside of it, it won't work. We'll go actually in our future labs in that direction, because it would really help us to predict more complex relationships, more complex geometries, and actually to extrapolate the values that are here. So this is it. That's what we've been doing in the recent actually years. And if you have any questions, or if you'd like to contact me, if this is interesting to you, please feel free to do. Okay.
Thank you very much.